In this class we are going to discuss about introduction of logic gates. So, as the name indicates, these are similar to our normal gates which allow or decay someone. So, for example, if you want to allow or deny anyone, if you are just using your doors, that means your gates. In the same way, to allow or deny these digital signals, logic signals, these logic gates are used. For example, if you are using any gate, so that gate particularly allows specific combination of input signals. Generally, these logic gates are used to define a Boolean expression. This whatever output of logic gate is there, that is a Boolean expression. So, these are the basic building blocks of any digital circuit. Simply we can say these are the main building blocks for any digital circuit design. If you want to design any digital circuits without logic gates, we can't design any digital circuits. So, now we will skip into how many types of gates are there, what are the logic gates, basic logic gates, and is there any other gates are there. Let us see here. So, see here we are having basic gates as 3 basic gates, those are AND gate, OR gate and NOT gate, and we are having 2 universal gates. Those 2 universal gates are NAND gate and NOR gate, and we are having 2 other gates like XOR and XNOR. So, now these are the names of logic gates. So, here why we are calling these 2 NAND and NOR gates as universal gates means by using these 2 NAND and NOR we can realize all other gates. For example, you can realize AND gate by using NAND gates combination. You need a couple or more NAND gates to realize AND gate. So, like that you can realize OR, NOT and XOR and XNOR by using NAND gate realizations. So, similarly by using NOR gates you can realize all other gates. So, that is why we are calling these 2 gates as universal gates. Now, we will see logic symbols. So, let me draw logic symbols for each and every gate here. So, for AND gate the logic symbol will be like this. So, this is the logic symbol for AND gate. So, it is having more than 2 inputs, it may have more than 2 inputs and only one output. Except this NOT gate, all other gates can have n number of inputs or excitations. We can say inputs as excitations and output as response. So, all gates can have n number of excitations and only one response. Always for any logic gate the response will be 1. So, that means only 1 in number, the response is 1 in number. So, here for example, I am taking 2 input gates, logic symbol for 2 input gates, you may have n inputs, just varies the input lines. For example, if it is symbol for 2 input AND gate, the 3 input AND gate may have 3 lines here, and n input AND gate may have n input lines at the input end. Here you may have n inputs. So, here this is a logic symbol for AND gate. Now, we are going for logic symbol for OR gate. So, for OR gate the logic symbol may be like this. So, this is the logic symbol for OR gate. So, here these 2 are inputs. So, you can say these 2 inputs like A and B, this is output Y. Similarly, for this OR gate these 2 are the inputs and this is output. So, similarly we are having logic symbol for NOT gate. So, I already told you for NOT gate there is only one input and one output. This output may be the complement of input. For example, if you are providing A here, your output Y is equivalent to A bar, that means complement of input we given. So, see here for NAND gate, NAND is nothing but not AND. So, complement of AND is nothing but NAND. So, here we are going with the same symbol as AND gate, with some NOT. So, this will provide you NAND gate. So, this is somewhat similar to AND gate. So, as I told you, NAND gate is equivalent to AND plus NOT. You are taking AND and NOT here. So, this will provide you logic symbol for NAND gate. So, see here, these are the two inputs A and B, and here output is Y here. So, now for NOR gate, the logic symbol is somewhat similar to OR gate with NOT. So, here the logic symbol for NOR gate will be like this. This is somewhat similar to OR gate with NOT. This is symbol for NOR gate. Here also we may have two inputs. So, as this is 2 input NOR gate, we may have 2 inputs and 1 output. You can observe here, for each and every gate the output is only 1. Only we are having 1 output. So, now we are going for other gates like XOR and XNOR. The logic symbol for XOR gate will be like this. So, here this is the logic symbol for XOR gate. Anywhere you saw symbol like this, you have to identify this as XOR gate. So, here XNOR, we can say this XNOR gate is complement gate for XOR gate. That means whatever here you are having as XOR gate, for that if you taken any bubble here, not here, it will gives you symbol, logic symbol for XNOR gate. So, here also we are having 2 inputs A and B, 1 output Y. Here also you are having 2 inputs A and B, 1 single output Y. Now, we will skip into truth tables. So, here we know that truth table is going to provide the input output relation. Truth table will define what may be the output of logic gate for particular combination of input. So, truth table always contains columns which is having inputs and outputs. So, here I am having inputs and I am having outputs in truth table. So, here in truth table, what are the inputs means whatever we are having at input of gate, that all you need to take at input columns. For example, if you are taking for AND gate or OR gate, what are the inputs means A, B are the inputs in each and every gate. So, truth table includes A and B in inputs column. So, we will take the combinations for that inputs. So, next in output, so whatever you represented at output, that you are going to take as output. So, by completing this truth table, by seeing itself, we can say what is the output for particular combination of inputs. So, now how many combinations we may have here? How many combinations means? So, 2 power n combinations we may have. So, this 2 power n, in which this n is equivalent to number of input bits. So, this is number of input bits. So, now for example, if you are taking 2 input AND gate, the number of inputs is 2. So, as our number of inputs is 2, you may have 4 combinations of that input. For example, if you are having 3 input AND gate or 3 input gate, you may have 2 cube combination of inputs in truth table. That means 8 input combinations you may have. That means A, B, C, you will get 8 combinations. Okay. Now we will skip into timing diagram. So, this timing diagram is also very important. Timing diagrams are nothing but diagrammatic representation of input and output. Diagrammatic representation of input and output. So, here low level will be represented like this. So, this is low level and high level will be represented like this. So, this is high level. So, high level will be represented in high pitch and low level will be taken at down. So, now by using this we are going to draw some timing diagrams. So, here for example, if you want to draw timing diagram for A, So, A is 0. After that, at a T1 time cycle A is 0, our A is 0, and T2 time cycle A is equivalent to 1. At T3 time cycle again it is pulled down to 0. For example, if you want to draw the diagrammatic representation of A, that means time cycle at each and every time period, first of all you need to take that time periods, that means T1 and T2 and T3. So, I am just taking the barriers like this. So, T1 is up to here, T2 is up to here, and T3 is up to here. So, now if you want to draw A, then A at T1 is equivalent to 0. I am just making this as 0. So, this is 0. And A at T2 is pull up to 1, that means it rises to 1. So, this is 1 here. So, now T3 at T3 this A value is equal to 0, that means again this is down to 0, the value here is equivalent to 0 here. So, this is called as timing diagram for a variable A. So, in the same way we can have different timing diagrams for all truth table variables, that means input output variables. So, in exams we may get questions on truth tables and timing diagram also sometimes. 1 mark questions we may get like this. So, they will simply give the functionality in truth table, they will provide the values in truth table. By seeing the values itself we have to say this is related to so and so gate, and similarly they will provide timing diagrams also. By seeing the timing diagrams, by observing the timing diagrams we have to say this is related to so and so gate. So, like this we are getting questions on this basic logic gates.